Alright, welcome to lesson 4. Today we're going to employ the definite integral as an accumulator function in context and understand and apply the rule for the definite integral of a constant function. Okay, so to discover some of these new concepts, go ahead and apply the knowledge that we already have about definite integrals to answer this problem. A ship sails at a constant rate of 7.5 nautical miles per hour, that's known as knots, beginning at 7 a.m. Let t represent the time since the ship took off, meaning t equals 0 corresponds to 7 a.m. Write and evaluate an integral to compute the distance the ship has traveled at 9 a.m. And B, define a function in terms of an integral that gives the distance traveled by the ship x hours after 7 a.m. Go ahead and complete that on your own, and then we'll take a look together. Alright, so in part A, I'm trying to calculate the distance that the ship has traveled from 7 a.m. to 9 a.m., or in other words, from when t is equal to 0 to when t is equal to 2. And I know the velocity function, it's a constant function, so v of t is equal to 7.5. And now I'm going to use the integral to evaluate or to represent the area underneath the velocity curve between 0 and 2. So now that I've represented this integral, I want to evaluate this integral, and I'm going to use the fact that I can interpret an integral as area. That's why I'm using it to begin with. So I'm going to go ahead and sketch a graph of the function and calculate the area between the curve and the t-axis in this case. Okay, so there's a sketch of my velocity function from 0 to 2, and this is just a rectangle with dimensions 2 and 7.5. Therefore, the value of my integral is just going to be 2 times 7.5 or 15. And in the context of the question here, I'm looking for the total distances traveled, so this would be 15 miles, and you would want to go ahead and write out that between the hours of 7 and 9 a.m. this ship traveled 15 miles. Before we move on to part B, I want to think about, in general, what would happen if you are taking the integral of a constant function. And when you think about this, you consider that a constant function is always a perfectly horizontal line. So when you're calculating the area under a horizontal line, you're always going to have a rectangle. Whether or not the constant function is above the x-axis or below the x-axis, it's always going to be a rectangle, where the height of the rectangle is going to be the value of the constant function, and the base is just going to be the length of your interval. So as you can see here, you multiply the length of your interval times the value of your constant function, and that's going to be the value of your definite integral. So this is something that we're going to apply to all constant functions, and we'll write this rule out in just a second. Let's go ahead and take a look at B now. In part B, we're going to write a new function in terms of an integral, and the function is going to give us the distance in terms of the number of hours x after 7 a.m. So my function, I'll call it d of x, and I realize that this is very similar to what I did in part A, except instead of being told the exact time at which we are evaluating the integral, x is variable, meaning that our integral isn't going to go from 0 to 2, it's going to go from 0 to wherever x happens to stop. So I can represent this in my usual integral notation, except that I'll have a variable as the upper limit of integration. So here we are. I'm going to take the integral from 0 to x of v of t dt, and of course v of t is a constant function, it's 7.5, so this is the integral from 0 to x of 7.5 dt. And we're interpreting this in context of area, and so we're imagining the area underneath my velocity curve, which is a horizontal line, and it's going to be determined by the value of x. And so you can imagine, as x begins to increase, we're going to be increasing the area. And the word for this is accumulate. So we're going to be accumulating distance as x increases. And that should make sense, obviously. Your ship is traveling at 7.5 miles per hour. So as the day goes on, you're going to be accumulating distance. Now we can apply what we just discussed with our constant function from 0 to 2, the integral from 0 to 2, to evaluate this integral from 0 to x. Because we're going to have a rectangle, we can evaluate the area of the rectangle by considering what the width and the height of the rectangle will be. The width of the rectangle is going to be the distance between 0 and x minus 0, which is just going to be x. The height of the rectangle is always going to be 7.5, so I'm going to multiply by 7.5. And what I can see here is that the function for the distance traveled by the ship is just going to be 7.5 times x. So representing this as an integral will help me understand what I'm doing, and then evaluating the integral will help me write this function in an easy-to-utilize format. Okay? This is what's called an accumulator function, because we're accumulating the area underneath our curve. All right, so let's go ahead and write down the theorem that we just discussed about the integral of constant functions. So if f of x is a constant function on the closed interval from a to b, then the integral from a to b of f of x dx is simply the integral from a to b of c times dx. And we can interpret the integral, the definite integral of a function, as in terms of area, right? The area that's above and the area that's below the x-axis. So I've drawn the two possible options that we have here. I can have a constant function that is a positive value or a constant function that's a negative value. And I bet you can guess how to compute the corresponding values of the definite integral. For a constant function that's positive, I know that the value of the integral is going to be positive, and it's going to be exactly equal to this area that is made up of a rectangle, where the width of the rectangle is b minus a, and the height of the rectangle is c, as I have shown right here. When my constant function is a negative constant value, we know that the definite integral is going to have a negative value since all the area is below the x-axis, and it's going to correspond to the negative of this area. And the reason that is going to be the case is because my c value here is going to be negative, so I'm going to compute this area in the exact same way, b minus a times c, except that a negative c will provide a negative result for my integral. So with that being said, I bet you can write down the missing piece here. The integral from a to b of a constant value c dx is going to be simply the value of my constant function times the length of the interval b minus a. One thing to note is, of course, that when my constant function is positive, greater than 0, this value is going to be positive, greater than 0. And when my constant function is negative, this value, the value of the integral, is going to be negative, just as I have written right here. All right, let's go ahead and take a look at the next thing which we discovered, the idea that we can write an accumulation function using an integral. We discovered the accumulation function in our discovery problem in the context of an accumulation of distance as represented by the accumulation of the area underneath our velocity curve. Now let's define it abstractly. So if we have a function f and it's integrable over the closed interval from a to b, then the definite integral of f from a to x defines a new function for x in between a and b called the accumulator function, written as a of x, or the accumulation in terms of x, which is equal to the integral from a to x of f of t dt. Now, you probably have a question regarding the multiple variables that are here. So you want to take a second to think about what each variable represents. That'll help clear it up for you. First, considering x, which is the independent variable of the accumulator function. In other words, it determines up to what point you're going to accumulate, and that's why it's the upper limit of our integral. T, on the other hand, is just a dummy variable, right? It's a placeholder that reminds us and illustrates how this product is constructed. And so T is going to take on every value from a to x. Remember how we discussed that infinitely many points that we're going to evaluate our product at, and then we're going to sum all those products together. To help illustrate how important it is that x and t be different variables, consider you are evaluating your accumulator function when x is equal to 5, meaning you would be running this integral from a to 5. Now, if x were 5 and this were f of x and not f of t, then you'd also be evaluating f of 5, which is just a value. So you'd be taking the integral of a constant function, which isn't the goal. You actually want to evaluate this product at every point from a to 5 and then sum all those products. So it's vital that you make that distinction between these two variables. Let's quickly look at a graphical representation so that we are clear on how this function works. So here I have a generic function f, and my accumulator function, evaluated at any value x, is simply going to look at the area from a to x between my curve and the x-axis, and that's going to be the output for my accumulator function. So if this were my particular x value, the accumulator function is going to basically accumulate all of this area, and that's going to be the output of my function. And as x increases, I'm simply going to be accumulating more of the area between the curve and the x-axis. For example, if x is over here, then I'm accumulating all of this area as well, and that particular green swath is going to be the output of my accumulator function. There's one last thing to note, and it seems, because of the name accumulator, that it should be as x is moving along the interval towards b, that the value of my accumulator function, the output of my accumulator function, is just always getting bigger. And it seems like that's the case up until this point, and that's obvious because the value of my function is positive. So when I look back at my Riemann sums, right, all of those products are going to be positive. However, once I pass this point, all of those products which incorporate the value of my curve become negative. And so all of these accumulations are actually an accumulation or an adding on of a negative value. Remember, that's how we interpret the definite integral. The area between the curve and the x-axis, above minus the area that's below. So if you evaluate your accumulator function out here, you'll actually be taking this green area minus this red area. If you evaluated your accumulator function here, you'd only have this green area. So the accumulator function here gives a greater output than it would out here. And that's an important thing to keep in mind as you're building these functions. All right, so go ahead and try this problem on your own first, and then press play, and we'll take a look together. All right, I read through this, and I notice a couple of things. I'm given the rate at which snow is falling. I know that the independent variable t is going to go between 0 and 5, since there's a 5-hour span, and it measures the time since snow started falling. And I want to create a function to model the total amount of snow that has fallen. So I'm going to need to write this function so that it calculates the area that's underneath my rate of change curve. So to go ahead and write this out, I'm going to call this a of x for amount. And this is going to be, I'm going to integrate this function here, and I'm going to integrate from the time it started up until the value of x that's chosen, because it's going to give me the amount at any time x. And what am I going to integrate? Well, I'm going to find the area underneath this curve. So I'm going to integrate r of t dt. And of course, I actually know what r of t is, so I can simplify a little bit further. So here I have my integral, and noticing, of course, that this is a linear function, I can go ahead and sketch a graph of my function and interpret the area using what I know about the area of that particular geometric shape that is formed. So now that I've sketched this linear function, r of t, I can tell that the area between the curve and the x-axis up until the point determined by the value of x is going to be a trapezoid. So now I can go ahead and label the appropriate dimensions and then use what I know about the area of a trapezoid to write this equation more simply. And so applying what I know about trapezoids, I'm going to take the average of the two vertical side lengths, 1 plus 2x divided by 2, and then multiply by the distance between those two parallel side lengths. Doing a little simplification gets me to x squared plus x, and so that is my accumulator function, and that's going to be defined for x values from 0 to 5. All right, at this point, go ahead and begin the homework, Unit 7.04.